Dear students, welcome back to my YouTube channel, SNAr Chemistry Tutorial. MC Chemistry. Okay, you can access my previous videos either from my website or from my YouTube channel. Today I am going to discuss with you some topic based on aromatic nucleophilic substitution reaction. Comes under the topic halogen compounds. Okay, the learning objectives are to understand the aromatic nucleophilic substitution reaction and what are the types of aromatic nucleophilic substitution and what is the mechanical difference between the two mechanisms, that is additional elimination and elimination-addition. What is mean by benzyne intermediate? So, directly going to the topic aromatic nucleophilic substitution, and we already discussed aliphatic nucleophilic substitution reaction. There are two types of mechanism, SN1 and SN2 reaction. And the same way, nucleophilic substitution on aromatic ring is less common, and it may not be possible to undergo SN1 reaction there because the dissociation reaction does not occur in aromatic halide. Because in SN1 reaction, first step, we already seen the formation of carbocation, and here the carbocation, that is a positive charge on benzene ring or sp2 hybridized carbon atom, is unstable. So, no possibility of SN1 reaction. Then, what is the other reaction? That is SN2. And in SN2, backside attack is taking place in aliphatic compound. But when coming to the aromatic case, the nucleophile cannot approach this carbon atom through the backside because here there will be a lot of electron density that on above and below the plane of the benzene ring. That benzene or the electron density can prevent the approach of a nucleophile. So SN2 reaction is also not possible in aromatic compound. So aromatic halide, suppose you have one or more electron withdrawing group positioned at ortho or para position, it is made it easier for the reaction. And suppose you have an electron withdrawing group here at ortho or para position, you have 3 examples here. It can activate benzene ring to nucleophilic substitution reaction. Why? Because this electron withdrawing group can decrease the electron density of the benzene ring. So a nucleophile can approach here. Okay, that is the reason. And in these 3 examples, you can see that when you have a number of electron withdrawing group increased from 1 to 2 here, electron withdrawing group, and 3, the conditions, the drastic condition, you can see here the reaction is occurring at 160. But you need to have only 100 degree if you have a 2 electron withdrawing group, and you need a 40 degree heat when you have a 3 electron withdrawing. So when you have a number of electron withdrawing group increased, the reaction becomes easier. So there are 2 types of mechanism, addition and elimination mechanism. This is also called SNAr, and elimination-addition mechanisms called Benzyne mechanism. Coming to the additional elimination mechanism, this is the general scheme of this mechanism. And here, the first step is actually attack by nucleophile take place. So it attacks this carbon atom, and it forms a sigma complex. Okay, it is called ipso attack, and it forms a carbanion sigma complex, and the halogen get departed to give the product after losing halogen. So, for example, when you have a paranitro and halide in the presence of a base, strong base, this base can attack this carbon and first addition takes place and it forms a sigma complex and this carbanion, and this carbanion was first observed by the scientist mesenchyma. That is why it's called mesenchyma intermediate. Okay, this is the first step, addition takes place. Second step is the elimination, and it's very fast, and elimination of halide takes place and form corresponding nucleophilically substituted product. And in the presence of base, this become oxide, and this can be protonated later. And this carbanion intermediate or mesenchyma intermediate is highly resonance stabilized. This is the actual resonance stabilized structure of that complex, and this is the first intermediate carbanion, and this carbanion is resonance stabilized like this. Transfers electron towards here and double bond break. Then this carbanion, this electron density withdrawn or delocalized over NO2 also. This has communication between benzene ring and nitro group. So it delocalized and it formed a four-resonating structure. And among this four-resonating structure, this one is highly reactive because you have a 2 negative charge on oxygen atom, and both oxygen atom, this is highly stabilized and intermediate. Okay, and the rate of reaction depends on the reactant aryl halide and nucleophile, so it's a bimolecular reaction. And when you have the substituent at para position, we already seen this is the intermediate, and stabilization of carbanion is achieved if you have an NO2 at either ortho position or para position. But when you have nitro at meta position, you can see that the delocalization to the nitro is not taking place. Here you can see this is only delocalization takes place over the ring only, not to the nitro group. So this is a stabilization of carbanion usually achieved only in ortho or para position. The electron withdrawing is at ortho or para position, not at meta position. That is very important point. And another point is actually if you have the incoming nucleophile should be stronger than the group being replaced. So this is the group we are going to replace. So the incoming nucleophile, if it is stronger, it can leave. Otherwise, the living group again will attack. So one more point here you have to understand is, in this case, why we are using fluorine here in the case of aromatic compound. So what is the role? Usually the living group, iodine is better living group. But here the reactivity gets increased in the case of fluorine. Do you know the reason? The reason is increase in electronegativity can stabilize the carbanion intermediate, because this electronegative compound can attack that carbanion and make it stabilized. So that is the reason here the fluorine is more reactive when you have a fluorine living group here. So over here, parafluoronitrobenzene, you get a paranitro-anisole. And another example, 1,2,4-dinitrobenzene with some more alkylamide, and you get N-ethyl 2,4-dinitro-aniline. So that's about addition elimination mechanism. Next one is elimination-addition reaction and its mechanism. And when you have an array halide without any electron withdrawing, how does it react with nucleophile? So it does not react with the nucleophile under normal condition, but do react under forced condition. So you need very high temperature here. So at very high temperature you get phenol, the chlorine gets substituted. And another strategy is if you are using bromobenzene, it can react with powerful base like potassium amide in liquid ammonia. If you are using this compound, you can get aniline, So this reaction takes place with a highly unstable intermediate called benzyne. So this is the mechanism of elimination-addition reaction. Here, first the elimination takes place. In previous case, it was addition takes place, then elimination. Here, it is different. Elimination takes place first and addition then. Okay, so when we are using very strong base amide, it can abstract this proton, trap this proton. Do you know what? Because this proton is very near to this highly electronegative atom, so it can inductively withdraw the electron, then it becomes acidic. The CH bond becomes acidic and elimination gives usually the carbanion. This carbanion and this bromine can kick off this carbanion and it forms a very highly unstable intermediate that's called benzyne. This is also called dihydrobenzene. Next one, benzyne can react with available amide base and it forms the amide NH2- can attack this carbon, benzyne, and the triple bond break and it forms a carbanion. You will get the double bond acid, and in liquid ammonia there is an ammonia. That ammonia can be proton here and it forms an aniline. So here you have one issue here. This benzyne, in some cases it was found that there is two types of product. One is directly substituted product. That means the amine gets substituted at the position where the living group is there. The another one is sine substituted product, that is the just adjacent to that the carbon having living group. So how do you differentiate this carbon? That was done by one experiment. C14 labeling experiment was done by J.B. Robert, and 1953, he labeled this carbon atom with C14, all other carbons are 12, and he found that the product he obtained is, in one case, the substitution is at labeled carbon, in another case, the substitution is at the sine carbon that is next to the labeled one. So in this benzyne case, this amide, the base can attack equally. There is an equal probability of attack at this carbon and this carbon, these two carbons. So if it is attacking here, you get this product. If this is attacking here, you get this product. So the aniline with equal proportion of compound was found. Okay, benzyne. Another example. And when you are using parachlorotoluene with amide, and it forms first a dehydrohalogenated product. Dehydrohalogenation takes place and the benzene will be formed, and the base attack in the next step, nucleophilic addition, and it forms a carbanion. Then the proton transfer takes place. And here you have the possibility of attack at this carbon and at this carbon. Okay, the first case was this carbon and you get this metatoluene, and when this amide attack this carbon, you get para-methyl-aniline. Okay, so it can attack here, and you get aniline NH2 here, and this get protonated to keep para-methyl-aniline. So next, the intermediate. How about the structure of intermediate? And benzene with this intermediate is actually benzene with carbon-carbon triple bond. How it's possible? Although it has a triple bond, it is not a normal alkane, like alkane. And out of these two pi bond here, one is normal pi bond, other one is actually formed by lateral overlap. And this orbital is little bit distorted part. So this one is formed by second pi orbital is formed by the lateral overlap of 2 sp2 hybrid orbital outside the ring. So this one is called normal pi bond, and this is abnormal pi bond. Okay. So the external pi bond is very weak, and because there is less overlap, so it is unstable and highly reactive. And what is the evidence for the formation of benzene? And you can do you get some evidence, like in the absence of very strong base, it was found that suppose there is a less availability of amide in the system. Once the benzene is formed, it contaminates. So that then this product isolated and characterized. So that is the indication that the product, the intermediate is structure, or the intermediate is benzene. And in next case, when furan is added here, it undergoes a cycloaddition reaction and it forms a desalted product like this. This is diene, this is tanophyl, and this can undergo 4+2 addition and form a cyclic product. So this is clearly indicating the formation of intermediate is benzene. And third one, when you add anthracene to benzene, the intermediate, you get the cyclic product. So these are the indication of whether the product, the intermediate formed is, benzene. And in summary, we have learned two types of aromatic substitution reaction, and addition and elimination reaction is called SNAr, and second one, elimination-addition reaction, it is also called Benzyne Mechanism. And in SNAr mechanism, mesenchymal complex or sigma complex, a carbanion intermediate was formed. It's bimolecular reaction. In elimination-addition reaction, usually when you have an benzene is unactivated, there is no electron withdrawal, and some forcing condition such as strong bases should be used. And in this case, highly unstable intermediate was formed, that is benzene intermediate. Okay, that's all. Thank you for watching.